Hello, mathematicians. Today we are going to discuss transformations, symmetries, and tilings. We're going to talk about these because math is the only subject that counts. My name is Jessica Johnson, and let's get started. Ephraim and Devonte use the rigid motion of rotation on their image, which comes to 180-degree rotation. Here are their original set of blocks. The students use a point of rotation probably about this point here. And they move the blocks, let's say, in a clockwise motion. When Ephraim and Devonte were supposed to do was to reflect the blocks over a horizontal line in the center of the blocks in the square. Add in the horizontal line in the middle of the square, which is called the line of reflection. Or it could also be called the mirror line. Labeling our blocks, the first set of blocks are called the object. Essentially, when you have a reflection, you are flipping the object, so our image will look like this. Notice that the green tangrams are all facing the same direction because we only flipped the tangrams instead of rotating them. In this slide, I want to try to explain the concept of if you have one line of symmetry, you have a symmetrical shape, even though there may be more than one line of symmetry. There are 6 shapes that have a line of symmetry. The rhombus is asymmetrical when we place a line of symmetry in the center of the rhombus. When we fold over the line of symmetry, all the sides of the shape must match exactly, then we know that this shape is symmetrical. To know that a shape is symmetrical, you only need to find one line of symmetry, even though this shape has technically more than one line of symmetry. A hexagon is symmetrical and has a line of symmetry along with 2 other lines of symmetry. Insert a line of symmetry vertically. When we fold the shape over the line of symmetry, the sides of the hexagon match up to make one shape, such as the trapezoid. The rectangle is symmetrical. Insert the line of symmetry horizontally, or you could insert one vertically. When you fold the rectangle over the line of symmetry, the sides match up, making one side. The isosceles triangle has a line of symmetry vertically. Insert a vertical line of symmetry. The shaped side will match up when folded over the line of symmetry, making it look like one shape. The semicircle has one line of symmetry vertically. The last isosceles triangle has a line of symmetry horizontally. And when you fold the shape over the line of symmetry, it looks like this. There are only 4 shapes that have rotational symmetry. What you need to ask yourself is which of the figures will be unchanged if I rotate them 180 degrees. These 4 shapes have rotational symmetry because I can rotate them 180 degrees and they will be unchanged. What if we rotated our shapes 90 degrees? This is what they would look like. Then rotate them 180 degrees. And then they look like our original shapes on the left-hand side. For rotational symmetry, I want to point out a neat little fact. Take one point on the rhombus, and then you want to imagine that you're drawing a line from that point to the center, because when you do rotational symmetry, the shape rotates around the center. And then finish drawing the line to the other side. If the other side looks just like the first point where you started out, then you have rotational symmetry. There are no shapes that have exactly one line of symmetry and rotational symmetry. Let me explain my answer. The first shape, as we discovered earlier, does not have a line of symmetry, but has a rotational symmetry, which does not meet both criteria. The rhombus has two lines of symmetry, and it has a rotational symmetry, but does not meet the criteria because it has two lines of symmetry instead of one. If we rotated the rhombus 180 degrees, it would look exactly the same. The third shape does not have a line of symmetry, but has rotational symmetry, and therefore does not meet the criteria of one line symmetry and rotational symmetry. The isosceles triangle has one line symmetry, but does not have rotational symmetry. The rectangle has two lines of symmetry and a rotational symmetry. This is the rectangle at 180 degrees with a rotational symmetry. Looks exactly the same, right? Because it has two lines of symmetry, it doesn't meet the criteria. The second shape, the isosceles triangle, has one line of symmetry but does not have rotational symmetry. The semicircle has a line of symmetry but does not have rotational symmetry. Let's check Meyer's work. When you are working with vertex figure, the interior angles in the middle, or the vertex, of the figure has to equal 360 degrees. The pentagon has 108 degrees for each angle. An octagon's interior angles equals 135 degrees. A hexagon has interior angles equal to 120 degrees. Sum the interior angles of each of the original figures of the pentagon, octagon, and hexagon. 108 plus 135 plus 120 degrees equals 363 degrees, which is greater than 360 degrees. Unfortunately, our friend Myra is not correct. She did not create a vertex figure. Now I want to apologize for this 180, it should be 108. Sorry. Myra needs to arrange her tangrams in a way that there will be a 3-degree gap. This gives Myra a 3-degree deduction. Therefore, the interior angles will equal 360 degrees. As we learned earlier, the sum total of the interior angles equal 363 degrees. With the 3-degree deduction, she will have 360 degrees. Triangle QPT is congruent to triangle SPT because of the line segment PT is congruent. Basically, line segment PT is the intersection of the figure. An intersection means that each side of the intersection are equal distances or values. In other words, PT is like a line of reflection, meaning that the triangle SPT is a mirror image of QPT. Also, triangle QPT is congruent with triangle SPT because the side-side-side theorem, which states that if the three sides of one triangle are respectively congruent to three sides of another triangle, then the two triangles are congruent. The next question is to show how angle QPT is congruent to angle SPT is true. Due to triangle QPT and triangle SPT being congruent, that makes our angles QPT and angles SPT congruent. Angle Q is congruent with angle S. Angle P from each triangle QPT and SPT are congruent. Notice that each angle that is congruent to each other, I am naming them together. Angle T from each triangle QPT and SPT are congruent. Why is triangle QPV congruent to triangle SPV? Triangle QPV is congruent to SPV through the side angle side theorem. V denotes our angle. Therefore, we are giving two sides and an angle. Side angle side theorem states that if two sides and an angle of one triangle are congruent, two sides and an angle of another triangle, the two triangles are congruent. Side QP is congruent to side SP. Side QV is congruent to SV. Angle V in triangle QPV is congruent to angle V in triangle SPV. And this is because of line segment PV is congruent to itself. Demonstrate why angle QVP is a right triangle. The angles QPV and SPV are adjacent. That means that each angle V from QPV and SPV are supplementary angles. Therefore, 90 degrees plus 90 degrees equals 180 degrees. For part A of question 5, we are asked to construct a regular pentagon, PENTA, penta. Part B asks that we construct triangle PQR. Part C asks that we inscribe the pentagon penta with triangle PQR. At this point, I'm going to ask myself, what do these have in common? Well, both images have the vertex P in common, making our new image look like this. Notice the pentagon and the triangle are sharing a common vertex. Then we are asked to calculate angle NOQ. First, look at the equilateral triangle PQR and the midpoint O. From here, we can see another triangle, an angle O, and that triangle POQ equals 120 degrees. The center of the pentagon has an angle of 144 degrees. Let me explain by pulling the pentagon out for just a moment. Divide the pentagon in a way that all of the angles in the center equal 360 degrees. Insert algebra, with each x equaling 72 degrees. 72 plus 72 equals 144 degrees. Therefore, the center angle of PON of the pentagon equals 144 degrees. To figure out what the degree angle of NOQ, take 144 degrees from 120 degrees, which equals 24 degrees. Two figures can be similar, even though they may not be the same size. Our textbook uses the example of a projector projecting a similar image on a screen, but it will be a larger image, just as the picture shown. After the smaller triangle, which is made between Jenny's eyes and ruler, has went through the projector, we have a larger triangle from Jenny's eyes to the cliff. It is similar to the smaller triangle, only larger. Label the smaller triangle ABC and label the larger triangle DEF. Triangle ABC is similar to triangle DEF, which means that angle A is congruent to angle D. Angle B is congruent to angle E. Angle C is congruent to angle F. The ratio will look like this. Side DE is similar to side AB. Side EF is similar to BC. And side DF is similar to AC. In summary, triangle ABC is similar to DEF. Angle A is congruent to angle D. Angle B is congruent to angle E. And angle C is congruent to angle F. And the ratios of the side of the triangles will look like this. DE over AB equals EF over BC equals DF over AC. Now to find the measurement of the height of the cliff. A mile is 5,280 feet. Divide 5,280 into 4 because Jenny is a quarter of a mile away from the cliff. And we get 1,320. Convert 1.5 inches into feet to equal 1.125 feet, or if you'd rather work with fractions, it's 1 over 8. Take Jenny's 2-foot arm and put it over 1,320. Put 0.125 over the cliff height. But wait, we don't know what the cliff height is. So let's figure it out. To find the cliff height, take 0.125 times it by 1,320, divide it by 2, and we get 82.5 feet. Thank you for listening to my presentation, and I hope that you realize that you really can learn anything. Thank you.